Hey guys, today I want to present a solution to Balkan Math Olympiad 2024 problem 4. Firstly, let's take a look at the problem statement. We are asked to find all f and p, where f is a function from the positive reals to the positive reals, p a polynomial with non-negative real coefficients and the constant term being equal to 0, such that f of x plus p of y is equal to f of x minus y plus 2y whenever x greater than y greater than 0 are both real numbers. First, I want to note that 2y is positive and in particular not 0, which implies that f of x plus p of y is not equal to f of x minus y. Therefore, these arguments are also not equal, which we can rearrange to p of y plus y is not equal to x minus f of x. We are free to choose y between 0 and x here. Therefore, since this is a continuous function, this left-hand side attains every value between p of 0 plus 0, which is 0, and p of x plus x. In particular, since p is greater than or equal to 0, it follows that the right-hand side can never attain any value in the interval 0 to x, and therefore we conclude that f of x must be greater than or equal to x. We can use this result to simplify the left-hand side of our given functional equation. So let me write down f of x minus y plus 2y is equal to f of x plus p of y. And now this is greater than or equal to f of x plus p of y. And applying the inequality again, we obtain that this is at least x plus p of y. We see that this inequality gives us a nice asymptotic upper bound on p. Namely, if we let d equal to x minus y be fixed, then we can rearrange this inequality to be p of y less than or equal to f of d plus y minus d. And now, since d is fixed, this can be a constant, maybe a large one, but that doesn't matter. If we now just take a very large y, then this tells us that p of y doesn't grow faster than linear. In particular, because the factor in front of the y is a 1 on the right-hand side, and because p of 0 equals 0, we conclude that p of x is equal to c times x for some c less than or equal to 1 for all positive reals x. Looking at our functional equation, it now looks much more tame because we just have a c times y here. Now we can try to think of what the possible solutions are, and we immediately see that it is possible to take c equals 1 and f to be the identity function. It is a good idea to check if there are any other solutions that we can find right away. For example, I would search for linear functions f, but we see that on the left, f is just applied once to x, whereas here we have an f of x plus something, and therefore the linear term should be 1, and also our constant is 0. So for now, we only write down that f of x equals x and p of x equals to x works. Unfortunately, it is not so clear how to proceed from here, and the following substitution is not the first idea that I tried. But I want to notice that we would like to prove that f of x equals x, and we already know f of x greater than or equal to x. Moreover, we have this y here, which is outside of any function argument. And for these reasons, we want to take a look at the function g of x, defined as f of x minus x, and try to prove that g is the 0 function. We now want to rewrite our functional equation using g instead of f, so we replace every f of x by an g of x plus x. Therefore, the left side becomes g of x minus y plus x plus y, and on the right we have g of x plus x plus cy plus g of x plus cy. Finally, we erase the x and y terms on both sides to obtain the equation g of x minus y plus 1 minus cy equals g of x plus cy plus g of x. We will now prove that the only g greater than or equal to 0 satisfying this equation is the 0 function. So let us denote this by qx, y. Since g is non-negative, we directly obtain three inequalities from this, and the simplest one is where we lower bound this by 0 to obtain g of x is less than or equal to g of x minus y plus 1 minus c times y. This inequality tells us that the growth rate of g is at most linear with the coefficient 1 minus c. Maybe a nicer way to write this would be by replacing x with x plus d, where d is equal to y. So we have that g of x plus d is less than or equal to g of x plus 1 minus c times d. Looking at q of x, y, we can now simplify the functional equation by upper bounding this term to obtain that g of x minus y plus 1 minus cy is less than or equal to g of x plus 1 minus c times g of x plus cy, and then plus g of x. Now we only have terms involving g of x or y on the right, and we can bring those y terms to the left to obtain that g of x minus y plus 1 minus c times y minus cy is less than or equal to 3g of x minus cg of x. This inequality implies a linear lower bound on g of x, as y was just an arbitrary positive real number less than x. So we can let y approach x from below, and then also use the fact that this term will always be non-negative to conclude that g of x is greater than or equal to x times 1 minus c times 1 minus c divided by 3 minus c. We wanted to show that g is the 0 function and c equals 1. One way to achieve the second goal is to show now that g grows sublinearly, because then by this inequality c must be equal to 1. Looking at q of x, y, we have a single g on the left and two g terms on the right, and by taking y sufficiently small, this quantity can become arbitrarily small as well. The second observation which makes this interesting is that the argument of this g is smaller than x and therefore also less than g of x plus cy. This is not the behavior we would expect from a nicely linearly growing function. Indeed, if we denote this factor by alpha, then we can use the fact that both these arguments are greater than or equal to x to conclude that g of x minus y plus 1 minus cy is greater than or equal to 2 times alpha x. Replacing x by x plus y, this is g of x greater than or equal to 2 times alpha times x plus y minus 1 minus c times y. And then if we let y go to 0, this is nothing but 2 alpha x. So we obtain from g of x greater than or equal to alpha x that g of x must be greater than or equal to 2 alpha x, and therefore by induction we get g of x greater than or equal to 2 to the power of n times alpha times x for any n, and therefore we have alpha equal to 0. So we have c equals 1, and our functional equation simplifies to g of x minus y is equal to g of x plus y plus g of x. Unfortunately, I erased that inequality, but recall that by bounding this term by 0 from below, we obtain now, since c equals 1, that g of x minus y greater than or equal to g of x. And therefore, the function g is monotonically decreasing. Now, if x minus y equal d is fixed and we let x and y go to infinity, then both arguments on the right also go to infinity. Therefore, g of d is equal to 2 times m, where m is defined as the limit of g of x where x goes to infinity. So we have proven that g of d is equal to 2m, but this doesn't hold only for this value for d, but for any positive real d, and therefore g is the constant function, and we have that m is equal to 2m, so g of x equals 0 indeed. Hence we have proven that f of x minus x is equal to 0, and also c equals to 1, and therefore this is the only possible solution, and we are done.